Alright, so welcome back to particle physics and the standard model. This is lecture 35, and in the last lecture we saw how nature actually does break the electroweak symmetry in our universe. We finished up on what could have happened if we had had dynamical symmetry breaking that explicitly broke electroweak symmetry, right. The dynamical symmetry breaking coming from chiral symmetry breaking, and then we saw that if that had happened we would not be getting the correct masses for the gauge bosons and the fermions, right. So, we took a somewhat non-intuitive route that nature has actually taken, which is spontaneous symmetry breaking, in particular via a mass square term in the potential that is actually negative, right. If that were the case, the potential would look like this. So that you know it is a downward facing parabola at the origin, and clearly there is a minimum that you can calculate, and we saw that it is called spontaneous symmetry breaking because there is a set of degenerate vacua or degenerate minima. The possibilities of the minima themselves enjoy the symmetry of the theory, but the actual vacuum picked by the field configuration can only take on one value, and this can only happen spontaneously, right. So, spontaneously the symmetry got broken. Ultimately this is due to initial conditions, right, and then we saw some physical examples of it, ferromagnets and so on, and then we also saw one more thing, that is that every time you have a scalar potential that has picked up a vacuum expectation value, it also contributes to dark energy and hence the cosmological constant problem, right. But we are not yet done with our goal of seeing where the masses actually come from, right. So, we have a mechanism for converting a field to a constant value, but where do the actual masses of the fermions and the gauge bosons come from, okay. So, to see that, let us make a couple of observations, okay, and I am going to write the Higgs doublet in this notation now. Remember, there is an imaginary part and a real part to each of the two components. I am going to give them names like these, you will see why in a second, okay. That is the upper element. What about the lower element? For that I am going to do something slightly suggestive. The real part I am going to write as V plus H, okay, and the imaginary part I am going to still call it a G, G3 in this case, and once again I am going to normalize this field with the square root of 2, okay. Why am I doing this? Because I want this H field to be some fluctuation around the vacuum expectation value, which is V, okay. So, here V is the constant, whatever the minimum is, in this case what was it, mu squared over 2 lambda, right, under a square root. So, that is what V is, and H is a field, okay. So, there are still 4 fields here, right, okay. So, this I can do basically without loss of generality. What do I mean? I could have put the V, I could have picked any of the 4 directions in field space to be where the vacuum expectation value is, right, but I am going to give it, I am going to put the vacuum at in the direction where the real part of this second element is, okay. That is all I have done. I could have put V anywhere basically, okay. Having done that, here are a couple of observations, okay. Observation 1, see at the vacuum, that is once the potential has relaxed to its minimum, okay, I am going to show that G1, G2 and G3 0, the 0 stands for electric charge, are massless. Okay. How do I do that? I have to look at the quadratic terms, right, of these fields. And how would the quadratic terms look like? Let us go back here, let us look at the potential. So, or let me just write the potential here for being self contained. Okay, so here is the potential, this is, I am going to write this explicitly now as minus mod mu squared. Earlier we just had mu squared, right, but we know now mu square is negative. So, I am going to write it this way, I have a h dagger h plus lambda h dagger h squared, that is the potential, no. Okay. Now, go back to this, plug in the h, parameterize this way, and you will find that the quadratic terms, okay, from the mu squared I have a G10 squared over 2, agreed, G10 squared, that is why I have a square root of 2, right, plus, will I get something from the quartic term? Of course I will, right. Again expand h now in this form, okay, and you will find that there is in the quartic term there is a G1 squared that marries the V squared over here, right, agreed, there is a cross term basically, right, and that would look like you will have a 2V squared. Why is that? In the cross term when you square it you will get a 2 outside, right, a plus b the whole squared basically, right, the 2ab part is what I am writing here. So, that is the quadratic term for G1 squared, plus of course dot dot dot, this is basically for G2 squared and G3 squared, okay. So, that is the mass, okay. So, mass of G1 squared, sorry, the mass of G1, if I square it, that is nothing but, what is it now, minus mu squared plus 2 lambda V squared. What is this? That is 0, right, that is exactly you know, when we minimize the potential, this is exactly what we got as a wave. So, I plugged in the V and I get it as 0, okay. So, again without loss of generality, that is also mg2 squared and mg3 squared, good. So, why did this happen? This is not a coincidence, okay. This is a consequence of a very, very important concept, Goldstone's theorem, okay. What does Goldstone's theorem say? It says that spontaneously broken, see all these words are important now, okay, continuous symmetries, okay, give rise necessarily to massless modes, okay. So, this is not specific just to the potential that we are talking about. You take any continuous symmetry, break it any way, in any which way, Okay, like even in the dynamical breaking that we saw earlier, even there you would have had Goldstone bosons. Okay, Goldstone modes. Of course, these are bosons. So, those massless modes are exactly what are known as Goldstone bosons. Okay. Not only that, how many Goldstones are there? In this case, there are 3, right? And how many when we broke SU2 cross U1, how many generators did we actually remove? So, how many generators does SU2 have? Has 3, SU2 has 3 generators, right? What about U1 hypercharge? That has 1 generator, correct? So, what we have done is not just break SU2 cross U1, okay, we have broken it down to something smaller actually. We did not break it completely, we have broken it down to electromagnetism, and we will see how this happens in a second. Okay. And how many generators does this have? 1 generator. Okay. In other words, for every generator of the symmetry that is broken, okay, there is 1 Goldstone boson. Goldstone mode, Goldstone boson, however you want to put it. Okay. So, does that tally here? We started with 4 and then ended up with 1. So, we broke 3 generators in some combination, correct? So, in this case 3 generators corresponds to 3 Goldstones. Okay. All of this falls under the Goldstone theorem. Massless modes arise when you have spontaneously broken continuous symmetries, and the number of generators broken is the number of Goldstones. So, everything works out there. Okay. Now, this is not the first time we are seeing this actually, okay. Although I have not mentioned it as such, in this course we have already seen this happen. How is that? In low energy QCD, okay, let us take the limit of massless up and massless down quark. Okay. In that limit, how would I write the Lagrangian of the quarks? Remember, this is a chiral theory, right? The left handed kinetic terms exist on their own and the right handed kinetic terms exist on their own, right? So, that means in 2 spinor notation, which is really the only notation that gives you a physical feeling for what is going on. Remember, this is how I would have written the maybe I am switching upper and lower indices, let me be consistent about that, right. That is for the up quark, and the down quark also I have something very similar, right. Right. Now, notice that this exhibits an SU2L times SU2R symmetry. Okay. So, this is not the Lorentz SU2 cross SU2. Okay. This SU2 acts on ULDL, right. Remember this is like isospin, right. In fact, this is exactly what will give rise to isospin. Okay. The isospin as we know it, and then this one acts on the UR-DR doublet. Okay. The right-handed ones act, the symmetry on the right-handed quarks act separately from the symmetry on the left-handed quarks. Okay. And what happens is that this is exactly what we saw as dynamical symmetry breaking. Okay. As the universe cools down, all right, you spontaneously break the chiral symmetry. So, as temperature goes down, you have dynamical breaking of chiral symmetry, which means this SU2 cross SU2R gives rise to SU2 isospin. Why? Because you formed quark condensates, quark anti-quark condensates. Remember? So, this is what acts on the proton and the neutron. So, when we studied isospin, Heisenberg's observation, etc., right, the flavor symmetries, all of it comes from basically breaking of chiral symmetry breaking dynamically. Okay. This is a very unique mechanism in nature where you do not have to do anything, nature does the breaking for you, that is why it is called dynamical. Okay. Okay. So, that may be so, but relevant to our discussion is how many generators are broken here? Would you agree that I start with 6 generators? Why? SU2 has 3 generators, right. So, I have 3 plus 3 generators, and in the end I end up with how many? 3 generators, right. So, how many generators are broken now? Three, right. So, that corresponds to how many Goldstones? We just saw by the Goldstone's theorem we need 3 Goldstone bosons, right. So, we do know that chiral symmetry breaks, right, and we do have isospin. So, all of this is true. So, where are the Goldstone bosons then? Where have we discovered the Goldstone bosons? The answer is they are exactly the pions. Okay. Remember the pi plus, pi 0 and pi minus, that is exactly what these 3 Goldstone bosons are. Okay. This is how we understand the formation of mesons. Okay. It is not just a quark anti-quark pair, that is what they are, right, Qi Qj in some bound state. It is not just that they form bound states, they arise exactly like this, they arise as Goldstone bosons. Okay. That is why pions are very, very special. But here is another reason why they are very, very special. Okay. I just said that the Goldstone bosons are supposed to be massless, right, correct. That is what the Goldstone theorem tells you, right. Spontaneously broken continuous symmetries give rise to massless modes, but the pions have a mass, right. The pions are all around 100 MeV, right, order of magnitude. So, what are we talking about here? How can they be Goldstones? The reason is that the quarks, right, are not massless either. Remember, when I said low energy QCD in the limit of mu and md going to 0, that is the limit where chiral symmetry is exact. Okay. Since mu is not equal to 0 and md is not equal to 0, but rather they are very small compared to the pion mass, at least compared to QCD scale, right. This would imply that chiral symmetry is approximate anyway. Okay. So, when you break an approximate symmetry, you are not going to get an exact Goldstone boson. What you are going to end up with is what are known as pseudo Goldstone bosons. If I had sent the quark masses to exactly 0, the pions would have been exactly massless, but since they are only approximately 0, the pion mass is also only approximately 0. Okay, that is why the pion gets a small mass. So, this is sometimes called pseudo Nambu Goldstone boson, because Nambu was also involved in treating these concepts in addition to Goldstone. Okay. And this is a good description, okay, because m pi is much smaller than mn and np, basically the QCD scale. Okay. So, this is a very good understanding of why the pions have how the pions arise and why they are not massless. So, this is a wonderful example of both dynamical symmetry breaking and explicit symmetry breaking. Why? Explicitly the masses not being 0 means the symmetry is already broken. Okay. Explicit symmetry breaking. But nevertheless we put it, we make it look like 0, and then we go ahead and do dynamical symmetry breaking, and then there is also an approximate symmetry breaking, right. So, it basically covers kind of everything you need to know about symmetry breaking. Okay. Alright. Now, let us go back to Electroweak symmetry breaking, which is a pure spontaneous symmetry breaking, right, and I am going to make my second observation about this. Okay, which is I am going to start deriving the masses of the gauge bosons. Where will I get the mass of the gauge bosons? When we introduced the Higgs field, the only terms we had were the Yukawa terms and the kinetic terms of the Higgs field itself, right. So, obviously this is where in the covariant derivative is where the gauge bosons reside. So, that is where I can hope to get the mass of the gauge bosons, right. So, let us write down the kinetic term after symmetry breaking, after spontaneous symmetry breaking. Okay. So, how would that look like? Okay. Now, here is how I am going to write this. I am not going to write all the terms, I am going to pick out only the terms that contain the masses that I want. Okay. So, I am going to write the H I am going to write as 0 and V, okay, because I know that the Goldstones do not matter here. The small h term will come to V plus H was there, right. I am just going to keep the V term for now in this expansion, okay. Then I am going to hit this with the rest of the covariant derivative, right, contains G1 B mu plus G2 W mu 3, or W3 mu rather. Okay. So let me get rid of this, and that's the 1 comma 1. Let me write the other diagonal element, G1B mu minus G2 W3 mu. Okay. So why did I get a minus? It's worth looking at it for a second. Let's again go back to the covariant derivative. See, here I have G1, right? What I should have actually done is put a the hypercharge. Okay, the hypercharge is already accounted for. Let me just write it in explicitly anyway. Okay, the hypercharge for the Higgs is 1 anyway. Okay, but then on one side I have a dagger, on the other I don't have the dagger, right? And that's why I pick up this extra minus sign. Okay. In the off diagonal, I have W1 mu minus I W2 mu. And in this off diagonal, I have W1 mu plus I W2 mu. Okay. Once again, let's go back here and make sure we are fine. Okay. Where did those things come from? So, so those things came from, I missed putting the generator here. The generator index has to be contracted, right? That's where that comes from. And the generators are what? Pauli matrices divided by 2, correct? So you can see that's exactly what would bring in the off diagonal elements. The first Pauli matrix picked up 1 under 1 here, the second one is I minus I, and then in the end the third one is 1 minus I, right? Good. So that's what brings the the minus sign here. So I stand corrected. So it's not the hypercharge, it's the third Pauli matrix that gives you a relative minus sign between the diagonal elements. Okay. Okay. Now that's on. So that's not all. Okay. There are more terms. So I'll write this and then look to wrap up the lecture. So it's worth writing all this. And of course I need to make sure that the Lorentz indices are contracted. So I'm going to put the indices upstairs. Again this is a minus G2 W3 mu, there is a G2 W1 mu minus in this case again W2 mu, okay, and the G2 W1 mu plus I W2 mu, okay. And of course in the end I have a 0 and a V again, okay. So I have explicitly picked from the kinetic terms the terms that would end up giving me masses, basically terms that are quadratic, okay. And I am neglecting, I am right now not writing the interactions of the small h field, right, the fluctuations, okay. Now I am going to do something here. I am going to define W minus, okay, as this combination of the complex fields, okay, plus I2, and I am going to define W plus as the orthogonal combination, okay. So I am going to wrap up by writing down the simplified version of this term, and I will let you look at figure out what the masses actually are, and in the next class we will take up exactly what the expressions for the masses are. Okay. So, with this definition you will find that this simplifies to 1/4 G2 squared V squared, there is a W plus and a W minus, but of course I have to contract the indices correctly, and a G1 squared plus G2 squared V squared. Okay. Now notice that there is one combination that picks up a mass in among the diagonals, right? Which is the combination that really picks up a mass? It is this combination, right? This is the combination that goes along for a ride with the V, not this combination. This combination seems to go have a 0 mass, right? So, let us write that combination down. So, I am going to write it in a slightly interesting way. Let me call it that minus sin theta W B mu squared. What does theta W stand for? I have just defined tan theta W as G1 over G2. Now go back and plug this in and convince yourself that this is exactly the combination that picks up the mass here, okay, from the Lagrangian. So I will leave you there, and in the next class we will see how to interpret this combination of fields as a whole other field. Okay? All right, thank you then, see you in the next class.